Hello everyone, Oleg is here. Welcome back to our calculus series. In the previous videos, we dived into sequences and sets as mathematical concepts. Today we'll switch gears a bit and explore how these abstract ideas translate into Python. Specifically, we'll discuss sequences, sets, and their operations in Python, focusing on the differences between mathematical concepts and Python data structures. For this video, I'll be using Jupyter Notebook, so we can see immediate outputs beautifully formatted and easy to follow. I'll be working with an environment with Python 3.13 to ensure we use the latest features. So let's start with the sequences. In mathematics, a sequence is an ordered collection of elements where order really matters. So here is the markdown with some definition. So both notations are equal. Sometimes sequences may be defined with curly brackets, sometimes with round brackets or parentheses. Doesn't matter. In Python, sequences may be represented by two entities, two main entities, maybe some others, some custom ones, but basically two. They are lists and tuples. So let me start with the list. So list is a mutable collection, meaning that we can change it after creation. For example, we can say list1, and this is defined as following. So this is list, and we can even print it. Or we can just do this without any printing. Jupyter will print it for us. So you can see that we have defined an ordered collection 1, 2, 3, and we can access each element by its index. So this is the 0th, this is the first, and this is not by the value itself. So we can collect anything like string 1, float, maybe an integer. The last one maybe something like other list or something. And we can see that we can address each element by its index. So the first element, or the 0th, Python starts with 0, is the string. The second one is the float. We can also address this from the end. For example, the first element from the end is another list. The second element from the end is 5, so on and so forth. And as I have already mentioned, lists are mutable. So this means that we can change the value of some elements. For example, we can say that the 0th element is going to be string 2 from now on. And we can see that the whole list has changed. So this is the sequence, as I have already mentioned. And we can check that these equations really work. And we can create list1 as 1, 2, 3. In Python, it's better to have a white space, and the second one will be 3, 2, 1, and we can check that they are not equal. So to check if two elements are equal, in Python you use two equal signs, and we can see that they are not equal because order matters, and lists, they preserve this order. The second way to preserve sequences in Python is using tuples. Tuple, on the other hand, are immutable, meaning that you are not able to change the elements after creation. So let's create some tuple. This will be 1, 2, 3. And yeah, we can see that tuple exists. We can check its type. So it's tuple. For the lists, it will be, of course, list. And we can check again that if we create another tuple with the same elements but in the other order, they will not be the same. So again, as I have already mentioned, the difference between the tuple and lists in general as a type is that you cannot change any element of tuple after it is created. For example, if you want to assign one of the elements, it will not be assigned due to an error. As a bonus in Python, when you define list, it allocates a bit more space than tuple in order to make sure it may be extended. For example, you can append values to the list, while tuple takes only the space in memory which was requested at the beginning, like 3 elements will be allocated, which is like a good bonus to save some memory just in case. So to conclude here, in mathematics, sequences are primarily about order, while in programming, lists and tuples add additional functionality like mutability in lists and immutability in tuples. These implementations allow us to model mathematical concepts with programming flexibility. Now let's move on to the sets. Set in Python is a collection of distinct elements where order doesn't matter, as we have discussed on the previous lectures. This is an example of how a set may look like. Again, curly brackets are 100% widely used in the set definition. So as I have already mentioned, sequence may be defined using curly and round brackets, parentheses, while sets are always defined with curly brackets. And let's try to create a set and check that the order really doesn't matter. So to create a set, you define it in either curly brackets or using the specific word called set. You can do the same with tuples and lists, by the way, but this one will be a bit shorter. So let's try 1, 2, 3, and the same for set 2. It will be 3, 2, 1. Let's see if they're equal. So hooray, yes. So this means that regardless of how you define sets, in which order they will be equal to the other. And we can even play with something more weird. We can define lots of elements in different way, and this has to be still equal to set 1, because the collection of distinct elements where order doesn't matter. So this is set. An interesting note is that set is like mathematical set is transformed into Python set directly without any changes in the naming, which is quite useful and handy. For the ordered sets, this is quite similar. So the ordered set in math, with some note, is translated into the same entity called ordered set. But an important thing is that Python doesn't have a built-in collection called OrderedSet, so that's why we have to install a specific third-party package. There are different implementations of sorted sets, and sometimes we really need a set where order of element really matters. For example, when you have a sequence of operations where uniqueness is required, but the order of appearance is also critical. And this is the case when we use ordered sets. As I have already mentioned, no built-in implementation, but you can use, for example, ordered set from the sorted collections. So let's try this one. We can take ordered set, and we can define the 1, 1, 2, 3, 1, 2, 3, 2, 1, whatever. And if we check, so we have to give it some collection, like a list. So you can see that it takes the elements according to how they were given. So the same order in which it was initialized. And it will be preserved after any operation with the set. So you can do any operations with the set, like adding values, removing values, and this will not break the order of the elements anyhow. For the classical set, this is not guaranteed. So we can check, for example, set 1, and we can add a value, for example, 10, and most likely this will be on the same position, but this is completely not guaranteed. So when you apply some operations like adding values or subtracting values in Python sets, the order of the addition or deletion of the elements is not guaranteed at all, because sets, they prioritize speed internally in the implementation. So that's why they do not care about the order, because the most important usage pattern for sets is the check if the element is a part of the set. So usually it doesn't matter how the elements were allocated. It's a bit different for the dictionary, by the way. But let's dive further. So we have talked about the ordered set, which is represented using some third-party collections. This may be ordered set from the sorted collection. Maybe others just use the one according to your preferences. They may contain some differences in the operations or some internal implementations, so please take this into account. Finally, let's talk about the operations. We'll start from the operations on sets. So let's look what operations or mathematical operations on sets are available in Python. So set operations in Python align directly with their mathematical definition. So let's explore each operation in detail, starting with union. I have prepared some visualization with the formula. So visualization is from Wikipedia, and the formulas I will explain in a bit. So what do we have on this image? On the image we have two sets. There are sets A and B. The set A is the left circle, the set B is the right circle. And on the image you will see that the red color means what we select and the white color means what we do not select. So here on the image you see that we select everything from both, from set A, from set B, and also what is inside them both, like the intersection of them both. So this is the union of sets A and B. Let's now look at the mathematical formula for this union. So A and cap sign B is equal to the new set. So A is a set, B is a set, and their union generates a new set. So these two definitions are equal. Let's look at the first one first. So the curly brackets again mean that we are generating a set, a resulting set. So we're generating the set which will have some x values, and such x, so this semicolon or vertical line means that x such that x either is a part of set A or x is a part of the set B. So basically the union of sets A and B is a set of elements x such that x is either part of A or x is part of B. So this is the union. So to conclude, like we can see that all elements from A are included, all elements from B are included, and the intersection as well. To show this in code, let's take again two sets. Set 1 will be 1, 2, 3. Set 2 will be 2, 3, 4. And we can define a union of sets in Python, in higher versions of Python, latest versions, in two ways. So the first one is symbolic. We use this sign to define the union. This is one. The other way is to do this using the union command. Union. So the result will be the same. So this is the union, and let's proceed to the intersection. The intersection looks similar, but we select only everything what is on the intersection of these two sets. Again, the left one is A, the right one is B. The intersection is defined as following. So these are the elements such that element is related or is a part of set A at the same time as it is a part of a set B. And in the same way, we can do this in Python in two ways. So set 1, we use this operand, oh sorry, not this one, and set 2, so we can see that elements 2 and 3 are on the intersection. And in the same way we can use, so quite useful sometimes on the projects to find the intersection of unique collections or unique sets. So the next one is the difference. So let's look at the difference. So the right set is B, the left set is A, and we're going to take everything from B which is not a part of A. So that's why B will be selected not completely. The part which intersects with set A will not be taken. As you may guess, and just in case, of course, the definition. So this is every x, we can, by the way, define it in a similar way. So this is this one. So again, this is every x which corresponds to B and at the same time doesn't correspond to A. All right. So again, difference between sets B and A is such a set where each x is a part of B, but at the same time not a part of A. And again, we can say this is the difference between set 1 and 2. Let's print them just in case. So 1, 2, 3 minus 2, 3, 4. So 2 and 3 will be deducted and only 1 will remain. And this, in the same way, we can do this with the operator difference. The result will be the same. Finally, last but not least operation is the symmetric difference, is the most unusual, I would say. So this is the way to select everything from A and B which is not on the intersection. So you can notice here a XOR operator. So basically we are going to take all the elements from sets A and B such that it is either A or B, but not in both at the same time. So this is the symmetric difference. And again, there is a specific comment for that. So again, let's remind us what are sets 1 and 2. 2 and 3 are intersections, so we're not going to take it. It's white, and we take only the red elements. This is 1 and 4. In the same way, we're going to make this with the operator. All right. These are the operations on sets. And again, an interesting highlight here is that these operations are pretty directly defined from the math. So the math operations, they look in the same way as they are created in Python. Let's switch to the mathematical operations on sequences. It's interesting that sequences do not have such operations like union, difference, and so on, because these operations are defined in mathematics for unique collections of elements, and that's why mathematical operations on sequences are a bit different. As we have discussed on the previous video, there are two types of operations on sequences. So the first one is pretty straightforward, is multiplication by constant. So let's assume that we have a sequence like 1, 2, 3, defined as a list. And we have some scale factor, like, I don't know, 10. So what we can do is that we can multiply each element from sequence by this number. This may be done in Python in various ways. The most Pythonic one is using list comprehension. So what we do, we say that we iterate over each element in sequence, and each element is multiplied by scale factor. And you can see that we'll get a list with elements scaled by the scale factor. We can do this in various combinations. For example, we can divide each element by the scale factor. Again, we can do everything like for each element correspondingly having a sequence. And you see the sequence, the sequential order of the elements is not changed at all, but we can apply some operation to each of the elements of the sequence. So this is one type of operations on sequences, for example, multiplication by constant, division by constant, and so on and so forth. So we can probably subtract from each element of a sequence some constant. The other type of operations on sequences involves two sequences. So let's have sequence 1 and sequence 2. So what we can do summation of both sequences or addition of sequences. For this, we have to use the operator called zip. So this is a very interesting operator in Python, which combines elements from multiple iterable collections, for example, sec1 and sec2, and gives them with their corresponding indexes. For example, it will give you at first 1, 4, secondly 2, 5, and so on. So we can iterate over pairs of elements. For example, this will be sec1 element, sec2 element in zip, and we can just look how this works. So you can see that we are using them like pair by pair. And we can apply several operations. For example, we can say that x plus y for x, y in zip, sec1, sec2. So you see that we sum two sequences element-wise. So 1 plus 4, 2 plus 5, 6 plus 3. And we can do the same for each operation. We can multiply, we can divide, we can subtract. For the division, it's a bit trickier because if you have 0 as one of your elements, so let's say we have some sequence with 0 elements, and we're going to divide. This will be division by 0 error, of of course, because we are not allowed to divide by 0. So these are about the operations on sequences. To conclude, today we explored sequences and sets in Python, comparing their mathematical roots to programming implementations. We demonstrated their operations, limitations, and some unique features. In upcoming videos, we will proceed with math. Thank you for watching.